May 1938, Europe's on the edge of war. Japan's tearing through China, and the U.S. Navy has a problem that keeps admirals awake at night. Every carrier fighter in service is obsolete. The Grumman F-3F biplane tops out at 260 mph, respectable in 1935, but utterly suicidal for the battles looming on the horizon. Intelligence reports from Spain's civil war are unambiguous. The new generation of fighters from Germany, Britain and Italy are hitting 350, maybe 370 mph. If conflict erupts in the Pacific, American pilots will be flying coffins. The Bureau of Aeronautics issues a specification in February 1938 that reads like a wish list written by someone who doesn't understand physics. They want a single-seat fighter that can hit 400 mm's, carry 4 heavy guns, have armor plating, self-sealing fuel tanks, and still land safely on a carrier deck at 70 mph without killing the pilot. It's an impossible dream, or so the skeptics say. But for Chief Engineer Robert Hall and his team at Chance Vought, impossible was just another word. They see opportunity where others see limitations. Hall envisions a sleek, low-drag monoplane powered by the new Pratt & Whitney R2800 engine. They sketch radical concepts. Long wings to generate lift at low speeds, a streamlined fuselage to slice through the air, and a cockpit that gives the pilot maximum visibility during takeoff, landing, and combat. Every curve, every line, every choice of material will matter. Even before the first prototype is built, engineers are pushing the limits of metallurgy, aerodynamics, and engine power. The clock is ticking. The Navy wants this fighter tomorrow, knowing full well that global tensions could erupt into a full-scale war at any moment. In a factory full of drafts, blueprints, and buzzing machinery, the future of American naval aviation is taking shape. One daring idea at a time. The challenge is monumental, but if they succeed, they won't just meet the Navy's impossible specification. They'll create the fastest, most capable carrier-based fighter the world has ever seen. By early 1939, Chance Vaught's engineering team had fully committed to translating Robert Hall's radical designs into something tangible. The specifications from the Bureau of Aeronautics were demanding, almost absurd. 4 heavy guns, armor, self-sealing fuel tanks, a 400 mph top speed, and the ability to land on a pitching carrier deck. To most engineers, this would be a nightmare. To Hall and his team, it was a challenge that would define their careers. The first obstacle was the engine. The Pratt & Whitney R2800 Double Wasp promised 2,000 horsepower, enough to push a sleek airframe past 400 mph. But packing that much power into a manageable, carrier-compatible design introduced severe torque issues. Early sketches revealed that without careful attention to weight distribution and balance, the plane could easily flip on takeoff or struggle during carrier landings. The solution required an innovative approach to the airframe and landing gear. The wing design presented another complication. Hall rejected conventional straight wings, knowing that lift, maneuverability, and clearance for the massive propeller had to be balanced. He settled on the now famous inverted gull wing, a radical departure that allowed the landing gear to be shorter and sturdier while giving enough propeller clearance. While it looked unusual on paper, this design became one of the defining features of the Corsair and a critical factor in its future success. Meanwhile, engineers faced material challenges. They needed lightweight aluminum alloys strong enough to withstand high-speed maneuvers and potential combat damage, while keeping the aircraft's weight low. They experimented with advanced alloys, reinforced joints, and heat treatments, often pushing the limits of what was considered practical at the time. Every pound saved contributed to the plane's speed and agility. Even with design solutions in place, the timeline was brutal. The Navy expected the first prototype to fly in just 14 months, a record-breaking schedule. Hall implemented strict division of labor. One team focused on airframe fabrication, another on engine integration, another on armament and systems. Communication between teams had to be flawless. Any miscalculation could cause months of delays. Prototypes were built while calculations were still being verified. A risky approach that demanded precision and confidence in every engineer's judgment. Testing protocols were equally intense. Scale models were wind tunnel tested, and stress simulations were performed to identify weak points before the first full-scale flight. Hall insisted that every component be inspected multiple times, ensuring that no oversight could compromise the aircraft. Yet the pressure didn't just come from engineering challenges. The political and military stakes were enormous. If the Corsair failed, the Navy's carriers would enter the Pacific with fighters inferior to what Japan was already deploying. Failure was unacceptable. Amidst all this pressure, Hall's team innovated in assembly techniques. Riveting, panel fitting, and engine mounting methods were rethought to save time without sacrificing structural integrity. Workers were trained to handle specialized tools, and every stage of production was streamlined. By mid-1939, the first airframes were beginning to take shape, towering over the factory floor like giant mechanical birds waiting to soar. Despite skepticism from outside experts and even some Navy officials, Hall pushed forward. His vision was clear. Create a fighter that could dominate in speed, maneuverability, firepower, and carrier adaptability. Every engineering decision, every late-night calculation, every adjustment to design brought them closer to producing the fastest fighter the Navy had ever seen. By the end of 1939, the Corsair was no longer just a concept. It was a tangible machine, ready for its first test flights, and the stakes had never been higher. If the team succeeded, they wouldn't just meet the Navy's impossible demands. They would redefine carrier-based fighter aviation forever. The first flight of the F4U Corsair arrived in early 1940, a tense moment that had the entire VOT team holding their breath. Chief Engineer Robert Hall climbed into the cockpit, strapping himself in with the knowledge that years of design, hundreds of calculations, and endless nights of work were about to be tested in the air. On the tarmac, the prototype's massive propeller roared to life, the powerful Pratt & Whitney R2800 engine vibrating through the fuselage. This was no ordinary plane. It was a promise, a gamble, and a revolution all in one. As the Corsair lifted off, early signs of its potential were immediately evident. It climbed faster than any Navy fighter had before, and the torque from the powerful engine, while challenging, was manageable with careful rudder control. Yet the first flight was far from perfect. The aircraft exhibited severe tailwheel shimmy, and the controls felt stiff at lower speeds. Hall and his test pilots made meticulous notes, documenting every nuance of behavior. They knew that the plane's unique inverted gull-wing design, while revolutionary for carrier landings, introduced unexpected aerodynamic quirks that needed refinement. Engineers worked tirelessly to address these issues. The landing gear was reinforced, and control surfaces were adjusted to reduce stress and improve handling during takeoff and landing. The R2800 engine itself required fine-tuning, with fuel injection systems calibrated to deliver smooth, reliable power throughout the flight envelope. Hall insisted on pushing the prototype to its limits in testing, stalling it, performing steep dives, simulating carrier landings, all under controlled conditions to understand every potential failure point. By mid-1940, the Corsair had undergone multiple iterations of flight testing. Each trial revealed both promise and peril. Its top speed surpassed 400 mph, astonishing everyone at the Bureau of Aeronautics. The aircraft could outclimb and outmaneuver nearly every other fighter in the Navy's inventory. Yet early prototypes also showed tendencies to bounce on carrier landings, and visibility over the long nose remained an issue for pilots. Every setback was met with rapid engineering solutions, wing flaps adjusted, cockpit height modified, tail design tweaked. The pace was relentless, but the Navy demanded results. Amid this high-pressure environment, pilot feedback became invaluable. Test pilots worked closely with engineers, sharing observations on torque behavior, stall characteristics, and dive stability. Hall encouraged open communication, recognizing that real-world experience was as critical as theoretical calculations. The Corsair's handling quirks, once feared, gradually transformed into tactical advantages, allowing skilled pilots to exploit the aircraft's speed and firepower in ways no other carrier fighter could. By late 1940, the Corsair was proving itself in high-speed dives, tight turns, and simulated combat scenarios. Critics who had once dismissed the plane as overcomplicated and doomed began to revise their opinions. The combination of raw power, innovative wing design, and precise engineering was yielding a machine capable of dominating the skies. The F4U Corsair had survived its early trials, but the real test was just beginning. Engineers had shown that speed and agility were possible, but production challenges, carrier suitability, and operational deployment would soon test their ingenuity to the absolute limit. The 14-month deadline loomed, and the team knew that any delay could mean entering the Pacific War unprepared. The stage was set. The Corsair had flown, and the engineers had proven that their radical design worked. Now they had to take it from prototype to a weapon of war, fast, reliable, and ready for the world's deadliest aerial combat. By early 1941, the Corsair was no longer just a prototype. It had become the focus of an all-consuming race against time. Engineers at Chance Vought were under enormous pressure. The Navy demanded a fully functional, carrier-ready fighter within 14 months. Any misstep could delay deployment and leave American carriers vulnerable to the increasingly aggressive Japanese Navy. Hall and his team knew that success would require not just innovation, but audacity. The most critical issue remained the landing gear and carrier suitability. Early Corsairs had demonstrated remarkable speed and maneuverability, but carrier landings were another story. The long nose and torque from the powerful R2800 engine made landings difficult. Even minor miscalculations could send a pilot into the sea. To solve this, engineers reinforced the landing gear with heavy-duty struts, adjusted shock absorbers, and reworked the gear's geometry to absorb impact while keeping the aircraft stable. They experimented with every possible combination of wing angle, flap deployment, and fuselage balance to ensure that the aircraft could land safely on a pitching deck. Another major breakthrough came with torque management. Pilots had reported the plane yawed violently on takeoff due to engine power. To counteract this, engineers added subtle changes to the tail and rudder design, improving stability without sacrificing speed. The Corsair's unique inverted gull wing not only provided propeller clearance, but also allowed for shorter, stronger landing gear that absorbed shocks and reduced stress on the airframe. These refinements, while small on paper, proved monumental in practice. Simultaneously, the armament was perfected. The 450 caliber M2 Browning machine guns were mounted in the wings, with precise calculations to ensure that recoil and vibration did not compromise accuracy. Engineers also worked on ammunition, feed systems, armor plating, and self-sealing fuel tanks, balancing protection and performance in a way few aircraft had achieved before. Every ounce of weight was scrutinized, every rivet considered, because speed, firepower, and durability had to coexist in a single airframe. By mid-1941, the Corsair had entered an intensive flight test regimen. Engineers and test pilots pushed the aircraft through extreme maneuvers, high-speed dives, vertical climbs, hard turns, and carrier landing simulations. Each flight revealed new data, feeding back into rapid design adjustments. The plane's performance astounded everyone. It outpaced existing Navy fighters and rival designs from Europe and Japan, establishing itself as potentially the fastest carrier-based fighter in the world. The Navy's skepticism began to waver. Observers who once doubted the plane's feasibility were forced to acknowledge its potential. The combination of Hall's engineering ingenuity, pilot feedback, and rigorous testing had produced a fighter that could dominate in speed, maneuverability, and firepower. Yet, despite these successes, production challenges loomed. Scaling up from prototype to mass production would require ingenuity equal to that used in the aircraft's design. Every factory floor, every worker, and every process would be pushed to the limit. The F4U Corsair was no longer just a plane, it was a statement. Against impossible deadlines, engineering skepticism, and the impending threat of global conflict, Hall and his team had created something revolutionary. The world's fastest carrier fighter had taken shape, but the true test, the Pacific War, was still ahead. Success would not only depend on the plane itself, but on the skill of pilots, the precision of manufacturing, and the relentless innovation of the engineers who refused to accept anything less than perfection. By mid-1941, the F4U Corsair had moved from prototype to pre-production, and the engineers at Chancevot faced a new set of challenges. How to transform a meticulously engineered prototype into a reliable mass-produced fighter. Every component had been tested and retested, but scaling up production was another matter entirely. The factory floor buzzed with activity, a symphony of hammers, drills, and welding torches, as workers assembled the first series of Corsairs under the watchful eyes of Hall and his senior engineers. One of the most pressing issues was quality control. The Corsair's speed and structural integrity depended on precise tolerances. Even a minor deviation could compromise performance or, worse, pilot safety. To ensure perfection, Hall implemented rigorous inspection protocols at every stage of assembly. Workers measured every rivet, inspected every panel, and tested each control surface. A single misaligned piece could mean disaster in the skies, and Hall demanded that no aircraft leave the factory without meeting his exacting standards. Meanwhile, engine installation posed its own difficulties. The powerful Pratt & Whitney R2800 Double Wasp was unlike any engine previously used in naval aviation. Mechanics struggled with its size, torque, and intricate systems, which required new procedures and specialized tools. Engineers trained workers on precise techniques for mounting, aligning, and calibrating the engine to ensure smooth operation. Every test run revealed additional tweaks, from fuel system adjustments to cooling modifications, all designed to maximize reliability without sacrificing performance. Assembly line innovation became critical. Hall recognized that speed was just as important as quality. The Navy needed these fighters in ever-increasing numbers. He reorganized workflow, optimized the layout of machines and stations, and introduced simultaneous multi-stage assembly. Sub-assemblies, wings, fuselage sections, tail assemblies were built independently and then joined with precision. This approach allowed faster production while maintaining structural integrity, something few manufacturers had achieved with such a complex aircraft. Armament installation was another delicate process. The 450 caliber machine guns, armor plating, and self-sealing fuel tanks had to be integrated without upsetting the aircraft's balance. Engineers calculated weight distribution down to the ounce, adjusting components and mounts as necessary. Each gun was test-fired to ensure accuracy and reliability. Even small details, like ammunition feed systems, were carefully checked, because in combat, the difference between hitting or missing could mean life or death. By late 1941, the first production Corsairs were rolling off the line. Engineers and factory supervisors watched with a mixture of pride and anxiety as the aircraft were transported to test fields. Pilots performed initial flights to verify performance, endurance, and handling. The results were encouraging. The Corsair exceeded expectations. Its speed, maneuverability, and firepower proved the radical design choices had paid off. Yet every flight revealed minor issues that required ongoing adjustments, from control surface sensitivity to engine response under extreme conditions. Through sheer determination, innovation, and relentless problem-solving, Chancefort had done the near impossible. They had created a fighter capable of dominating the skies while meeting the Navy's unprecedented specifications. The F4U Corsair was ready for war, a revolutionary aircraft that combined speed, firepower, and durability in a way no other carrier-based fighter had before. The stage was now set for the Pacific Theater, where the Corsair would prove its worth in the crucible of combat. By early 1942, the F4U Corsair was no longer just a marvel of engineering. It was ready to face its ultimate challenge: combat deployment. While production lines churned out more aircraft, the Navy began intensive training programs to ensure pilots could master this radical new fighter. The Corsair's speed, torque, and unconventional wing design demanded a different kind of pilot skill than previous carrier-based aircraft. Every maneuver, from high-speed dives to tight turns and carrier landings, required precision and understanding of the machine's unique characteristics. Training squadrons were established along the East Coast, with instructors handpicked from the Navy's most experienced pilots. The emphasis was on acclimating pilots to the Corsair's power. Many seasoned aviators found themselves struggling with torque-induced yaw during takeoff, or the long nose that obstructed forward visibility. Landing on a pitching carrier deck was particularly daunting. Even a slight miscalculation could result in a catastrophic crash. Engineers and pilots worked closely, exchanging data and feedback, refining flight techniques, and making minor adjustments to control surfaces and flaps to improve handling. Simultaneously, combat strategies were being developed to leverage the Corsair's extraordinary capabilities. Intelligence reports from the Pacific Theater highlighted the need for aircraft capable of both dogfighting Japanese Zeros and providing effective ground support. The Corsair's combination of speed, climb rate, and heavy armament made it ideal for both missions. Pilots were trained in formation flying, dive bombing techniques, and high-speed interception tactics. Simulated combat exercises pushed pilots and aircraft to their limits, ensuring they would be ready for the real-world challenges ahead. Engineers continued to refine production aircraft even as they left the factory. Early operational models underwent rigorous sea trials, carrier deck tests, and high-speed intercept runs. Each trial revealed minor adjustments needed. Cooling systems were fine-tuned to prevent overheating during sustained climbs, armor plating was reinforced in critical areas, and fuel systems were optimized for maximum efficiency. This iterative process ensured that when the Corsairs reached frontline units, they were battle-ready and reliable under extreme conditions. By mid-1942, the first squadrons equipped with Corsairs were deployed to the Pacific. The pilots who flew them quickly recognized the aircraft's superior performance. Its ability to outclimb, outrun, and outmaneuver enemy fighters gave American forces a decisive edge. The Corsair's firepower, combined with its speed, allowed pilots to strike effectively and retreat before the enemy could respond. In the hands of skilled aviators, the F4U became a game-changer, instilling both confidence among Allied pilots and fear in their adversaries. The engineering ingenuity that went into the Corsair, its reinforced landing gear, inverted gull wing, and powerful R2800 engine, proved essential in combat conditions. Pilots relied on these design elements to survive carrier operations, long-distance missions, and aerial dogfights. The aircraft's durability was equally impressive, absorbing damage that would have grounded other fighters, allowing pilots to return to base and continue the fight. As the Pacific War intensified, the F4U Corsair emerged not just as a technological achievement, but as a symbol of American ingenuity, resilience, and determination. Every mission flown, every pilot trained, and every aircraft delivered reinforced the Corsair's reputation as the fastest, deadliest, and most reliable carrier-based fighter in the U.S. Navy's arsenal. The stage was now set for the Corsair to demonstrate its full potential in combat, where engineering brilliance and pilot skill would combine to redefine naval air superiority. By late 1942, the F4U Corsair had reached the front lines of the Pacific Theater. Its first operational units were assigned to Marine Corps squadrons in the Solomon Islands, where Japanese forces were entrenched, and air superiority was fiercely contested. The pilots arriving at Henderson Field quickly realized that flying the Corsair was unlike anything they had experienced. Its blistering speed and climb rate allowed them to intercept enemy aircraft before they could reach Allied positions, while the powerful R2800 engine demanded respect and precise control during high-G maneuvers. The first combat missions were both thrilling and terrifying. Pilots learned quickly that the Corsair's design quirks, the long nose, torque on takeoff, and sensitivity at lower speeds, could be deadly if mishandled. Yet, when mastered, these same features became advantages in battle. Experienced aviators exploited the Corsair's acceleration and dive capabilities to outmaneuver Japanese Zeros, often catching them by surprise in vertical dogfights. The aircraft's 450 caliber machine guns made short work of enemy bombers and fighters alike, delivering devastating firepower with remarkable accuracy. The Marines were particularly impressed by the Corsair's durability. Unlike earlier fighters, it could sustain damage and remain operational. One pilot recounted returning from a mission with bullet holes through the fuselage, wing damage, and a partially disabled tail. Yet the aircraft landed safely. This resilience, combined with its offensive capability, quickly earned the Corsair the nickname, the Angel of Death, among Japanese forces. Training continued even under combat conditions. Pilots refined tactics for escort missions, dive bombing runs, and ground support. Engineers remained in constant communication, analyzing flight logs and combat reports to implement incremental improvements. Adjustments to engine calibration, control sensitivity, and structural reinforcements were made almost daily. The combination of rapid feedback from the field and responsive engineering made the Corsair a constantly evolving weapon, adapting to the harsh realities of warfare in real time. One of the most notable aspects of the Corsair's early combat record was its kill ratio. While initially thought to be too complex or difficult for carrier operations, the aircraft demonstrated unprecedented effectiveness. Enemy aircraft found it nearly impossible to match the Corsair's speed and climb rate, and pilots learned to use energy tactics, diving, climbing, and sprinting to dictate the terms of engagement. The plane's presence alone shifted the balance of air superiority in the Solomons. Beyond aerial combat, the Corsair proved invaluable in ground support missions. Its speed allowed it to arrive on target quickly, and the heavy armament made strafing runs devastating against Japanese fortifications, supply lines, and transport vehicles. The aircraft's rugged design ensured that it could withstand anti-aircraft fire and still return to base. These operations cemented the Corsair's reputation not just as a fighter, but as a versatile, multi-role aircraft capable of reshaping the dynamics of the battlefield. By the end of 1942, the F4U Corsair had moved from experimental prototype to a proven instrument of war. Pilots praised its speed, maneuverability, and durability, while engineers celebrated the successful application of years of innovation under pressure. The aircraft had already begun to rewrite the rules of naval aviation, demonstrating that engineering ingenuity, when paired with skilled pilots and tactical innovation, could create an unstoppable force in the air. By early 1943, the F4U Corsair had become a symbol of American air power in the Pacific. Its reputation was spreading among both Allied and Japanese forces. Pilots in newly formed squadrons arrived at airstrips across Guadalcanal, New Georgia, and the Solomon Islands, where the Pacific War raged with intensity. Every mission highlighted the Corsair's combination of speed, firepower, and durability, proving that it was not only a fighter, but a versatile tool capable of turning the tide in aerial and ground engagements alike. The first major test of large-scale operations came during escort missions for bombers. Japanese fighters consistently attempted to intercept U.S. bombers attacking strategic positions. Corsair pilots learned to fly in tight formations, using their speed to shield slower bombers while aggressively engaging enemy aircraft. The Corsair's climb rate and dive speed allowed pilots to dictate the terms of engagement, making it nearly impossible for Zeros to gain the upper hand. These missions reinforced the importance of discipline, coordination, and energy management in air combat. In addition to escort missions, the Corsair excelled in ground attack roles. Marines deployed it to strafe enemy positions, disrupt supply lines, and neutralize artillery emplacements. The 450 caliber guns, combined with bombs and rockets when available, wreaked havoc on Japanese installations. Pilots reported returning from missions with their planes riddled with small arms fire, yet still operational, a testament to the aircraft's rugged construction. The Corsair's resilience instilled confidence in its pilots, knowing that even under heavy fire, they had a fighting chance to return safely. The aircraft also sparked tactical innovation. Pilots developed new maneuvers to exploit the Corsair's strengths. Steep dives followed by rapid climbs, high-speed slashing attacks, and coordinated team strikes that overwhelmed enemy formations. Engineers continued to fine-tune the aircraft based on feedback, adjusting control surfaces, optimizing the engine, and reinforcing vulnerable points identified during combat. This close collaboration between designers and pilots ensured that the Corsair remained not just a machine, but an evolving weapon capable of adapting to the dynamic challenges of war. By mid-1943, the Corsair's dominance became undeniable. Japanese forces nicknamed it the Whistling Death, due to the distinctive sound of its powerful engine slicing through the air. Allied commanders increasingly relied on the aircraft for both air superiority and ground support, confident that it could accomplish missions that older planes could not. Its combination of speed, climb rate, firepower, and durability made it uniquely suited to the harsh conditions of the Pacific theater, where terrain, weather, and enemy defenses posed constant threats. The Corsair also began to reshape pilot expectations. New recruits trained specifically for the aircraft, learning to harness its power without falling victim to its quirks. Lessons learned from early combat missions, torque management, landing techniques, energy tactics became standard training procedures. Veteran pilots passed down insights, creating a growing body of tactical knowledge that enhanced the effectiveness of every squadron. By the end of 1943, the Corsair was no longer just a technological marvel. It was a battle-tested weapon that had proven its worth. Its combination of raw power, versatility, and reliability gave the Allies a critical advantage in the Pacific, demonstrating that innovation, when executed under pressure and refined through experience, could produce a fighter capable of dominating the skies and redefining naval aviation. By late 1943, the F4U Corsair had firmly established itself as a dominant force in the Pacific theater. Its reputation was not just built on speed and durability, but on the exceptional results achieved by pilots flying this revolutionary aircraft. Mission after mission, Corsairs intercepted Japanese fighters, escorted bombers, and conducted ground attacks with lethal efficiency. Its kill ratio quickly became the envy of other Allied aircraft, cementing its status as one of the most effective fighters of the war. Corsair pilots began accumulating extraordinary combat records. Experienced aviators, utilizing the aircraft's superior climb rate and dive speed, developed aggressive tactics that left Japanese Zeros struggling to keep up. They executed high-speed slashing attacks from unexpected angles, then climbed back to altitude before the enemy could respond. The combination of tactical innovation and the Corsair's exceptional performance allowed pilots to maximize their survival while inflicting devastating losses on the opposition. By the end of 1943, several pilots had already achieved ace status, with multiple confirmed kills in a single engagement. In addition to dogfighting, the Corsair proved invaluable in close air support operations. During amphibious landings on islands like Bougainville and New Georgia, Corsairs provided precise strafing runs on entrenched Japanese positions, neutralizing machine gun nests, artillery, and supply depots. The aircraft's rugged construction and self-sealing fuel tanks allowed it to absorb enemy fire and return pilots safely to base, a critical factor in sustaining prolonged operations in remote Pacific locations. Pilots often reported returning with bullet-riddled fuselages yet fully operational controls, a testament to the aircraft's ingenious engineering. The integration of the Corsair into carrier operations also evolved during this period. Early concerns about the aircraft's long nose and torque during takeoff were mitigated through pilot training and slight design refinements. Carrier-based squadrons mastered the delicate approach, landing, and deck handling, allowing the Corsair to operate from both land bases and aircraft carriers with remarkable efficiency. This versatility meant that the aircraft could be deployed wherever it was needed most, providing critical air cover for both ground troops and naval operations. The Corsair's growing legend was reinforced by numerous daring missions. Pilots engaged in long-range patrols over hostile territory, often outnumbered, but never outmatched. Coordination between flight groups allowed multiple aircraft to execute synchronized attacks, overwhelming enemy formations. The combination of pilot skill and aircraft capability created a psychological advantage. Japanese forces quickly learned to fear the whistling roar of a Corsair approaching from the sky. By the end of 1943, the Corsair had become more than a fighter. It was a symbol of American ingenuity and determination. Every mission flown highlighted the careful balance between engineering excellence and pilot expertise. Engineers continued to refine production models, incorporating lessons learned from the field to ensure each aircraft was battle-ready. Pilots, in turn, adapted to the aircraft's nuances, pushing its capabilities to the limit. Together, they created a synergy that made the F4U Corsair an unmatched force in the Pacific. The legacy of these missions and the pilots who flew them would endure long after the war, influencing aircraft design, pilot training, and combat tactics for decades. The F4U Corsair had proven that innovation, resilience, and adaptability could produce not just a successful fighter, but a game-changing weapon that dominated the skies and secured American air superiority in one of history's most challenging theaters of war. By mid-1944, the F4U Corsair had become a cornerstone of Allied air power in the Pacific. Its speed, firepower, and durability allowed pilots to dominate the skies, providing air superiority that was essential for both strategic bombing missions and amphibious landings. Veteran pilots had honed their skills over countless sorties, mastering the aircraft's quirks and exploiting its strengths to devastating effect. Every mission reinforced the Corsair's reputation as not just a fighter, but a reliable, lethal, and versatile weapon. The aircraft's impact extended beyond the battlefield. Engineers and designers had proven that seemingly overcomplicated technology could succeed under pressure, and pilots demonstrated that skill and adaptability could maximize an aircraft's potential. Squadrons flying Corsairs achieved kill ratios unmatched by other Allied fighters, and stories of dogfights, daring raids, and heroic returns became legendary. The plane's durability allowed pilots to survive encounters that would have grounded or destroyed lesser aircraft, making it a trusted companion in the most dangerous missions. The legacy of the Corsair was also a human story. Pilots who survived the Pacific theater carried with them memories of courage, innovation, and teamwork. They had pushed both themselves and their aircraft to the limits, proving that engineering brilliance paired with skilled aviators could change the course of war. The lessons learned in the Pacific influenced post-war aircraft design, carrier tactics, and pilot training programs for decades to come. Ultimately, the F4U Corsair was more than a machine. It was a testament to American ingenuity, resilience, and determination. A fighter that redefined naval aviation and secured the skies for Allied forces. Its combination of speed, firepower, and survivability made it one of the most iconic aircraft of World War II, a symbol of technological triumph and the courage of the pilots who flew it. The Corsair's story reminds us that innovation and bravery together can achieve the extraordinary, leaving a lasting mark on history.